Now let us start with a new discussion, and this discussion will be based on specific heat and and how do we define this physical quantity as specific heat of any substance. What we say is that specific heat of any substance is defined as that heat which is basically required to raise the the temperature of 1 gram of substance through 1 degree Celsius. And this specific heat is not always constant, but it varies, it shows variations with temperature. And if we go back to kinetic theory of gases, if we talk from kinetic theory of gases point of view, now according to this theory, the mean kinetic energy of each degree of freedom, degree, degree of freedom of a gas molecule at any temperature, say T, this degree of freedom is equal to, the mean energy that's associated with 1 degree of freedom is equal to 1 by 2 kT, where this K is Boltzmann constant. And for if we assume a monoatomic gas, there are 3 degrees of freedom for a monoatomic gas. So the average kinetic energy that we will have per molecule will be 3 by 2 kT. All we have to do is to multiply this average kinetic energy per degree freedom of a molecule by 3. So this is giving us 3 by 2 kT. Now, if we talk about a solid, we may assume at this point of time that a solid it consists of some individual atoms. Let's take it like this. If we assume that it consists of some individual atoms which are bound to their neighbors, but they can resonate and vibrate freely when we heat them. We supply them some heat, they can oscillate freely, and they can vibrate freely. And if we take on n as Avogadro's number, as we know, this Avogadro's number will give us the number of atoms in a gram molecule. It will give us the number of atoms in gram molecule, in 1 gram of a molecule. Then we can think of multiplying this number with 3 by 2 kT. And we have this K from kinetic theory of gases. This K is R by N. Now, if this is the case, we can think of using it here, and we will get N times 3 by 2 kT. For K, I will use R by N T. So this N and N is going out, so we will have 3 by 2 RT. And at the same time, if we assume that this mean potential energy that there exists between these atoms in this solid, which has three components of vibration, and if we take on that also equal to 1 by 2 kT, uh, and we average it over 1 by 2 kT, and we take it same uh, as that of the mean kinetic energy of the atoms in this solid, then what will be the total energy? So I should write here total. Oh, let me go with the potential energy. So what that potential energy would look like, that would be 3 by 2 n k t, and take it equal to 3 by 2 RT. So what we are trying to say here is that the average kinetic energy of the atoms in this solid, we take it equal to the average potential energy of these atoms in this solid. So now we can think of the total energy. We can talk about the total energy of these atoms in this solid. So total energy, that must be kinetic energy plus potential energy. So this total energy must be 3 by 2 RT plus 3 by 2 RT. So this total energy will be 2 times 3 by 2 RT. And this 2 and 2 will go, and we will get 3 RT. And if we make use of this value of gas constant R equal to 1.9856, and per gram atom, and what we find is this E nearly comes out to be 3 times 1.9856, and this nearly comes out to be 5.96, right? So the value for E that we get here in terms of calories, it is 5.96 calories per gram atom. Now, this treatment was considered as a theoretical proof of early law that was given by Dulong and Pettit. And what Dulong and Pettit law states, it states that the heat capacity per gram, heat capacity per gram atom of most of the solids, categorized most of solids, is nearly equal to 6. And if I have to define this specific heat with respect to this equation, that specific heat at constant volume can be defined as the derivative of the total energy with respect to temperature. So taking E as 3RT, what we will have is RT3. So what we will have is 3R. So specific heat, as we calculated from the basic assumptions using Boltzmann's average kinetic energy, and what we got is this specific heat of solids at constant volume is nearly coming out to be 5.96. So I think here I am committing the mistake. This is CV. Okay, so this is CV. So CV is 3 times 1.9856. This 1.9856 is the gas constant. So the value that we obtain here is 5.996. And the law that was proposed by Dulong and Pettit, what they predicted is that this CV, this specific heat at constant volume, for most of the solids is nearly equal to 6. However, the law fails completely. I mean, it fails completely when we are applying this law to the light elements like carbon at low temperatures. And what we see is that the specific heat varies with temperature, and it tends to go down to zero. And if I have to roughly indicate the behavior of specific heats, this behavior, this is my temperature in Kelvin, and if this is my atomic heat. So, so what we see is that there is a variation with respect to the temperature, and this is an approximate curve for diamond. And for silver, it goes like this, and then it goes like this. So this is for silver. And for lead, it goes like this. So the very fundamental argument of Dulong and Pettit is appears to be wrong here, because when we see the variation of this specific heat, the atomic specific heat of these solids, it does not have a constant value. It keeps on changing. And this failure of law could not be explained by classical theory, which basically assumes that this body that we have, the solid that we have, it absorbs heat continuously, indefinitely, in all formats. So it is apparent that the fundamental assumption of the classical theory is at fault. So, in order to explain the specific heat of solids, we have Einstein's model that we would like to discuss in the next video, where this basic assumption is turned down, that this heat is continuously absorbed by the solids.